This is a good theorem.
Yeah, we should know the statement of the theorems as well.
Yeah. I have finished my work. How is your preparation going on for the quiz?
It's going on, ma'am, going on well.
Okay. Have you been to such quiz contests earlier? What sort of questions do they ask?
Last year we had gone for the same event, ma'am.
Okay.
There was a round where they gave us some famous theorem statement, but they had missed out on some of the hypotheses. And the people, the contestants were asked to find out what the hypothesis that is required to prove the theorem and all that.
Oh, that's fine. Then you must be very thorough with the statements of all important theorems.
Yeah, we are going through.
So you have prepared well on this aspect for this quiz.
Yes, ma'am.
Okay, then let me ask you a question. Can you state the mean value theorem for differential calculus?
Yes, ma'am, I can say. Let f be a real valued function from closed interval ab to r,
Yes, sir.
which is continuous on the full interval a comma b and differentiable in the open interval a comma b. So continuous on closed ab
Yes.
and differentiable on open ab.
Yes.
Then there exists a point c in the open interval such that f dash c means the value or of that function, the value of the differential at that point will be f of b minus f of a by b minus a.
Yeah, it is
the
this result which you need to answer my question. What is the question? Should one's instantaneous speed at any instant during his travel be exactly the same as his average speed?
Yeah, I think I got the clue now, ma'am.
Okay, fine.
I also got it.
Suppose f of t at any time t in the open interval AB is the distance travelled by him in the interval closed interval a comma t. Then f is a continuous function of t in the domain of f that is closed interval a comma b.
Yes, write down what is his average speed.
So his average speed will be f of b minus f of a by b minus a.
Yes, you are right. So, now by mean value theorem,
Yeah.
right?
Now by
There exists an instant, say t, which I call as c, which belongs to the open interval AB, such that df by dt evaluated at t equal to c is f of b minus f of a divided by b minus a. So, it says his instantaneous speed is exactly the same as the average speed at the instant t equal to c.
Yes.
Yes, madam.
So, this answers my question in affirmative.
Yeah.
Yes, ma'am.
Is it clear?
Yes, ma'am.
Sure?
Yes, ma'am.
Okay. Then what happens in the case of a finite set of numbers?
There are 50 students in a class and we are saying we are calculating their average marks. Say 25 of them got 84 and 25 of them got 86. So their average will be 85 but none of the student will actually be getting 85.
Yes.
So in the discrete case that value may not be attained at some point, but in the continuous case The mean value theorem is saying that the value will be attained at some point.
The average speed, right,
Yeah.
is the same as the instantaneous speed at some particular instant during his travel.
Yes,
That's happening in the continuous case. Yes, you are right. In fact, I have another interesting observation. Suppose say a man X travels 10 miles in 1 hour. Then what is his average speed? It is 1 mile per 6 minutes.
Yes.
Is that right? My claim is that during his travel, he has covered a distance of 1 mile in exactly 6 minutes.
This sounds really very interesting. The mean value theorem says that the actual speed coincides with the average speed at some instant.
Yeah.
This
Let's see.
question is much further than that. He has to cover actually that distance in that time.
Yeah. So let's see how it is done. Suppose say S is the distance covered by him along his path and measured in miles starting from the point where he started.
Okay.
And let f of s denote the time taken by him in moving from s to s plus 1, where s takes values in the closed interval, say 0 to 9. So let's see how it can be done. Suppose say s denotes the distance covered along his path in miles, measured in miles from the starting position. And let f of s denote the time that he takes in moving from s to s plus 1, where s takes values in the interval 0 to 9.
Yes.
So now I compute f of 0 plus f of 1 plus etc. plus f of 9.
Yes.
What do I mean by f of 1? F of 1 is the time taken to go from 1 mile to 2 mile.
Yes.
That's what it means.
Yes.
So I consider this sum f of 0 plus f of 1 plus etc. plus f of 9, which means he has travelled from the starting point to the first mile to the second mile, etc., etc., from the 9th mile to the 10th mile.
Yes, ma'am.
So we said that he covers it in
1 hour.
1 hour.
Yes.
So this must be equal to 60 minutes.
Yes.
Correct?
Yes.
So now, if all these 10 terms take values less than 6, then what can you say about the sum? It's going to be less than 60.
Yes.
If all these 10 terms take values, say greater than 6, then what can you say about the sum? The sum is going to be greater than 60.
Yes.
So now I have a function f, which is a continuous function defined on the interval 0 to 9, which is such that it takes values both less than 6 and greater than 6.
Yes.
In other words, I have values s1 and s2 such that f of s1 is less than 6 is less than f of s2.
Now I can complete, ma'am.
Okay,
Yes.
so she always requires some clues, right?
So now we have that f is a continuous function.
Yes, fine.
And so I'm going to use the intermediate value theorem that we have already learned.
Right.
So now by the intermediate value theorem, there exists an S0 in this interval S1 comma S2 such that f of S0 is equal to 6.
Yes.
So this says that there exists a point S0 such that in exactly 6 minutes the man has travelled from S0 to S0 plus 1.
Yes, you are right.
So this is another interesting application of the intermediate value theorem.
Yes.
So what about the average value of an infinite set of numbers? say my x is belonging to the closed interval a comma b, and I am taking the fx as its function value. So what will be the average of fx for these x belong to a comma b?
So you want to see the average of this f of x for x belonging to the closed interval a b.
Yes,
Yeah, one way of doing this is to divide this interval a b into n equal subintervals.
Okay.
So, of length b minus a divided by n, and let xi be a point in the ith subinterval,
Okay.
and you now compute the following sum, namely 1 by n into sigma over I f of xi. This I can write as 1 by b minus a into b minus a by n into sigma over I f of xi. So, if I denote b minus a by n by delta x, then this sum is 1 by b minus a into sigma over I f of xi multiplied by delta x.
Yes.
So, do you recognize this sum now?
Yes, this is the Riemann sum.
Exactly. So, this is the Riemann sum. And then, what is its limit when delta x tends to 0?
That will be the Riemann integral.
Yes, it is the Riemann integral. Namely, it is 1 by b minus a into integral a to b f of x dx.
Yes.
So, here is the answer. We define the average of f of x for x in the interval a b as 1 divided by b minus a integral a to b f of x dx.
This definition resembles the definition of taking the average of a finite set of values.
No, there is a significant difference between the two.
Is it?
In the case of discrete set of numbers, the average need not be one of the numbers. Right? You recall the example that Kuntal gave you.
Yes.
That may happen in the case of discrete set of numbers. On the other hand, in the case of a continuous function f from a b to r, the average value of this function over that interval a b is one of the values of the function f of x for x in a b. I am sure you know this result. A continuous function on the closed and bounded interval is bounded.
Yes.
We know. And in fact, it attains its maximum and minimum also.
Exactly. If I denote the minimum by small m and the maximum by capital M of the function f of x defined on the interval a b, then you know that m is less than or equal to f of x is less than or equal to capital M for every x in this interval a b. And you also know the following result. If f of x is less than or equal to g of x for x in the interval a b, then integral a to b f of x dx is less than or equal to integral a to b g of x dx. You also know this result.
Yes.
So now m integral a to b dx will be less than or equal to integral a to b f of x dx is less than or equal to capital M integral a to b f of x dx.
Yes.
So this gives us m into b minus a is less than or equal to integral a to b f of x dx less than or equal to capital M into b minus a.
Yes.
Or we have m less than or equal to 1 by b minus a integral f of x dx between a and b, and that is less than or equal to capital M.
Yes. So we have shown that the continuous function f attains the value small m and capital M, and the value 1 by b minus a into integral a to b f of x dx lies between this small m and capital M.
Yes.
So again, by the intermediate value theorem, there exists a value c
Yes,
in between a and b, that is in the interval a b, such that 1 by b minus a into integral a to b f of x dx is equal to f of c.
Yeah, it is equal to f of c.
Yes.
Right? Is it clear? So, what does this mean? The average value
Is
is
actually
attained
some-
at one of the values of the function f of x for x in the interval ab.
Again, we are using the intermediate value theorem.
Yes, intermediate
So it
value
has
theorem
so
is very
many
powerful.
applications,
It
yeah.
has lot of applications. Okay, so what's the time now? You said you have to go for the quiz.
Yeah.
Yes, ma'am, it's 12 o'clock already.
Okay, so have you prepared well? You are thorough with your preparation?
Yes,
Then
ma'am.
wish you all the best. I think we'll close our discussion for today with this.
Okay.
And then we shall continue with our discussion in the next session.
Okay.
Right? Wish you all the best. Do well.
Yes.
Yeah.
Yes.